thermal fluid sciences experts. This is ProReadyEngineer.
So specific heat relates to our day-to-day life. The concept of specific heat is actually very simple. It's the amount of heat or energy you need to provide to heat something 1 degree, and that something will be 1 kilogram, right? This is how they made this property. Now, I know this may not have come across as easy, but actually it will be in a second. You see, if you take 1 kilogram of water, so take a 1 liter bottle, fill it with water. That's 1 kilogram right there. How did I know that 1 liter is 1 kilogram? You know that from my presentation earlier when I spoke about the density. Take this 1 kilogram, put it in a pot on your stove, turn the heat on. Measure the temperature. Keep heating up. After the temperature increases 1 degree Kelvin or 1 degree centigrade, the amount of energy that went into the water will be about 4 kilojoules. So 4 kilojoules are needed to increase the water temperature 1 degree. Measure the temperature and wait until it's 10 degrees. At around 10 degrees, you have added amount of energy that is roughly 40 kilojoules. Because it's 10 degrees. You put in 40 kilojoules. You see, you'll tell me, but you are saying there water specific heat is 4.18 and you are using 4. Well, that's what I taught you today. You want to be extremely successful and just crushing it is when you simplify the numbers and reach an estimate that is reasonably accurate in a couple minutes. I have worked with people in my professional career who are in advanced roles, and we will be having a chat, and someone in particular comes to mind, but I'm not going to say any names. I'm not trying to embarrass anyone, but someone who is like very influential and working at very in very advanced, he has an advanced position, and I did an estimate in 1 minute. And he was struggling, we need to put the numbers together. We need to put the number in an Excel sheet. Let's just do the math. I told him, well, I just did the math for you. This is what it is. And when he went and put the numbers in an Excel sheet, he came back with a number that was somewhere between 5 to 10% different than what I estimated in 1 minute. Just while we are chatting. This is the power of doing order of magnitude analysis. This is the power of knowing what the numbers mean and be able to use them to do quick estimates and quick validations and quick designs. So let's say 4 kilojoule per kilogram for the water. Now, where does CP, this specific heat concept, comes into play? When you go to the sea, it comes into play. You see, early in the morning, let's say it's 9 a.m., you're taking a walk. You touch the water and say, boy, the water is cold. 10 a.m., water is cold. 11 a.m., water is cold. See what's going on? The sun is up. And the sand you are walking on is hot, is picking up the temperature. Air feels warm. You touch the water, it's cold. The opposite happens at night. Sunset happened. It's dark. You are taking a walk. Air is a little bit chilly. You touch the water with your foot and what's going on? This water is warm. It's 8 p.m. It's 9 p.m. The sand is cold. Air is cold. Water is warm. This is all specific heat. You see, air specific heat is 1. You just need 1 kilojoule and temperature goes up right away 1 degree. Water takes 4 times that. So it takes tremendous amount of time, all day long with the sun up. The sea is absorbing heat, and it's going up in temperature. And it takes a while for the heat, all that heat consumed to dissipate. But the air is changing very quickly. Let's say you're going to build a heat exchanger. Now, I know some of you may not be comfortable with the term heat exchanger, but these are an extremely important device. They sit in your own home. You know that water boiler in your basement? That's a heat exchanger device. You know the AC as a heat exchanger device. They are everywhere, heat exchangers there. You know, in your car, radiator, that's a heat exchanger device. And on and on and on. Now, let me tell you, heat exchangers are very simple. As the name implies, just think about the name. Heat exchange. Something is exchanging heat with something. You are either trying to heat something up or cool something down. Depends on what you are trying to achieve. Here's the fun part. If you are using water to cool something, or using air to cool something, the size of that device, or water is running to cool something, will be maybe 1/4, 25% of the size, where you are using air instead of water to cool something down. And let that sink in. Why is that? It's very simple, because of the specific heat. Water can absorb tremendous amount of heat for a very small increase in temperature. Cools down very good compared to air. Specific heat is a beautiful concept and very important for us to know, understand, and digest. You see, there's a CP and CV. And the difference between them is that process I just explained. Actually, if it's a liquid or solid, like water, or solid, like a piece of metal, it's very reasonable to say, well, it doesn't matter if pressure is constant or volume is constant. These are incompressible. It's the same number. A CP is a CV is a C. Now for gases, the situation is different. The story is different for gases. Gases, if you do this experiment I just said, they will be different if you are holding pressure constant or holding volume constant. They will be different because it's compressible and it's going to expand, it's going to change in volume. And in fact, the ratio of CP and CV for gases is important. It's called gamma, and it's an important number in thermal sciences. So there's another piece of information I want you to know, that this CP or CV is not necessarily a fixed number. It may actually change with temperature and pressure. Depends on your application. But using an average number works perfectly fine for engineering design purposes. So how is it measured? Well, you can think of what I just said, and this is where it comes into place. They call this device calorimeters. Couple examples are on the screen, and essentially Bump calorimeters, they are more of used for LHV, heating value measurements, but the concept is the same because you're trying to hold the volume constant. So relates to the CV, and the DS calorimeters, they are more of used for CP measurements,